So we have 3 talks today. The first one, Neta will talk about eliminating spurious states with induction axioms. So we have 20 minutes, 17 minutes for the talk, 3 minutes of questions, and we have too many questions. We'll have to cut it a bit short. When you're asking a question, feel free to introduce yourself if you want to. And yeah, I forgot to say, I'm Julia Belakova. I work at Purdue University now. Take it away, please. Thanks.
Thank you, Julia, for the introduction. And hi, everyone. Thank you for coming to my talk. I'll try to make it not too technical, because as Julia said, we're after lunch, and everyone a bit tired. So today I'm going to talk about using first-order logic as an abstract modeling language, the spurious states that might arise from this abstraction, and how to deal with them. So let me set the stage. We have a system that we want to verify, and first we need some specification that models the system. And for this specification, we need some specification language that is, on the one hand, amenable to automation, so we can automatically check some properties of the specification of the system. And on the other hand, we want this language to be rich enough to actually capture the true behavior of the system, the true semantics of the system, as precisely as possible. And one language that fits the bill is first-order logic, and specifically quantified uninterpreted FOL, with which we can specify complex and complicated behaviors and then verify them. And to drill a bit deeper, the specific setting I'm interested in is FOL-based deductive verification. So we have the system spec, and we have some properties that we want to verify that the system holds. And we have annotations that help us verify these properties. And we take all of that and we construct a verification condition, a VC, which is basically a formula in FOL that asks, can the system misbehave? Does the system have any bad behavior? And we take that formula and we give it to some FOL prover, like an SMT solver, and we can get either unsat, meaning the system cannot misbehave, and thus it is verified, or we can get sat and a counter model showing us a bad behavior of the system. But since we used FOL as an abstraction for the true semantics of the system, we need to ask, is this counter model true, or is it a spurious artifact of the FOL abstraction? And if it is a spurious artifact, we might want to refine the FOL abstraction to make it capture the true semantics of the system more precisely. Okay. So one way to refine the abstraction of the system is to use induction axioms, and I'm going to talk about that a little bit. And then I'm going to give our 2 contributions in this regard. One is how we use the spurious counter models in order to refine the semantics of the system, to automatically guide this refinement. And then I'll give some decidability results for a fragment of formulas in FOL, where this refinement process is complete, and we can precisely capture some non-standard FOL semantics. Okay, so let's start with a simple example, a simplified verification condition from the correctness proof of Paxos. So Paxos is a distributed consensus protocol where nodes in a network propose values over rounds, and they try to agree on a value. But for this simplified VC, we're going to have 2 sorts. Rounds and values. And in Paxos, we think of the rounds as natural numbers, but for this abstraction, we'll just use an uninterpreted sort and have some total strict order over it. And we have this proposal mechanism. So for every round and value, we can propose V on round R if either V is deemed safe, or there's a witness previous round W of R where V was already proposed. And this safe V predicate, so in Paxos it's a complicated condition, but for this simplified VC, it's enough to know that there can only be one safe value, so any 2 safe values are the same. And we want to prove that there can be only one proposed value, so we're going to take the negated Skolamides property that there exist 2 different values that were both proposed, and we want to see that the conjunction of all of the above is unsatisfiable. And this will verify that the system is correct. But unfortunately, there is an infinite counter model for this verification condition. So we have in this infinite counter model 2 values, the safe V1 and the unsafe V2. And we have infinitely many rounds, starting with R1 on the left up to R2 on the right, with infinitely many of those purple rounds between them. And V1 was proposed on R1, and V2 was proposed in all other rounds. And the reason it was okay, according to the proposal mechanism, to propose the unsafe V2 is that every round where V2 was proposed has a previous round where V2 is already proposed. And these W functions form an infinitely decreasing chain of rounds where V2 is proposed. So I gave you a little second to look at this infinite model, and you might say, well, we didn't want this model, right? We wanted the rounds to be the natural numbers, and the natural numbers do not exhibit this behavior, right? There's no infinitely decreasing chains of natural numbers. So what happened? Well, the FOL abstraction didn't capture a key component of natural numbers, which is that they are well-founded, meaning every subset of the natural numbers has a minimum. And this notion of well-foundedness is also related to finiteness when we consider a total order, since in a total order, finiteness is the same as bidirectionally well-foundedness, which means every subset has a minimum and a maximum. Okay. So we have this problem. We have the standard semantics of FOL, but in these standard semantics, we can't define well-foundedness, and we can't distinguish in general finite and infinite models. So what can we do? Well, the common wisdom is to add induction axioms to capture or to refine the semantics of FOL towards our intended semantics. So we can use induction axioms to refine the abstraction. So we have this axiom schema that says for any formula psi with a free variable x, if there exists some x where psi holds, there's a minimum x where psi holds. And this is valid in all well-founded and finite structures. So it's sound to add this axiom. And for finite structures, we also have this axiom saying that if there exists an x where psi holds, there is a maximum x where psi holds. And in fact, we can generalize a little bit and allow psi to have additional free variables and then universally quantify over them. So if psi has, in addition to x, y free variables, we can just say for all y, if there exists an x such that psi xy, there exists a minimum x such that psi xy. Okay. So we have our standard semantics of FOL and we have our intended semantics. And using these induction axioms, we can kind of bridge the gap between them. We can refine the FOL abstraction towards our intended semantics. And that's great. We can just start adding axioms. But the search space for adding axioms is huge. We need to find some formula psi with which we could instantiate our induction axiom schema, and we want some psi that will actually help us prove to verify our system. So what can we do? And this leads us to the first contribution that we have here, which is using the spurious counter models to automatically guide this refinement. So we saw this infinite counter model, and we might want to examine it in order to know which kind of properties to use with our induction axioms. But first, we need a way to hold this infinite structure in our hands. And in our previous paper from POPL' 2024, we introduced the notion of symbolic structures, which allow us to finitely represent this infinite model. So here, instead of the infinitely many purple rounds between R1 and R2, we have this one summary node that summarizes the infinitely many rounds between them. And whenever a symbolic structure violates some semantics, so in this case, well-foundedness, we'll have at least one summary node where we can pinpoint this semantic violation. And we can examine the properties of this summary node in order to instantiate our induction schema, our induction axiom schema. So Where can we start? We take this symbolic structure, and we can see that the summary node satisfies this unary property that propose x and v2. And we can generalize this to the unary property propose any v, where v is free. And we get this induction axiom that says for every v, if there exists a round where v is proposed, there's a minimum round where v is proposed. And when we take this induction axiom in conjunction to the VC we saw before, it becomes unsat, and we can verify the system. And this can be done automatically. So given a verification condition, we can automatically construct a symbolic model for it, a symbolic counter model, I would say. And we can examine the summary nodes within this symbolic model, see what kind of unary properties they satisfy. We can generalize these properties, replacing round terms with free variables, and we can use these generalized unary properties in order to instantiate our induction axiom schema. Okay. So that was the practical side. What about the theory? So an immediate question might be, can this be complete? Can this process of refining the F1 abstraction be complete and allow us to precisely capture our intended semantics with these induction axioms? And I think the obvious but unfortunate answer is no. We know there's no complete proof system for first-order logic for finite models. This is a known result from Trachtenberg. And also, there's no complete proof system for well-founded models. And I think I don't have a citation for that, but this seems harder than the finite question. So obviously, this is also not possible. But I promised you some decidability results, so what do I have? So in our previous paper, we introduced the fragment of OSC, ordered surf cycle, which is a strict superset of the effectively propositional fragment, EPR, of FOL. And it relaxes some of the quantifier alternation restrictions that EPR makes. So if we have two sorts, round and value, in EPR, we can have this quantifier alternation. For every round, there exists a round. For every value, there exists a round. This is OK in EPR and also in OSC. But this kind of self-cycle is, for every round, there exists a round, is disallowed in EPR, but is allowed in OSC. And the VC of Paxos that we saw is in OSC. And because of these self-cycles that OSC allows, there's no finite model property in OSC. So some satisfiable formulas in OSC only admit infinite structures. But what we proved in our previous paper is that every satisfiable formula in OSC has a symbolic model within a finite set, finite computable set. So we can find infinite models for formulas in OSC. And this means that satisfiability of formulas in OSC under standard semantics is decidable. So what about other semantics? So again, as I said, there's no finite model property in OSC. And this means that well-founded semantics and finite semantics are distinct from standard semantics in OSC. So this is in contrast to fragments like EPR, where you have a finite model property, which makes all of these different semantics coincide. This does not happen in OSC. But we proved that this induction axiom refinement process is complete for OSC. And the set of axioms needed in order to refine the standard FOL semantics towards finite or well-founded semantics is finite and in OSC. So we can take the formula, add all of the needed axioms, and we get all of the needed axioms by characterizations of summary nodes in the candidate symbolic models. And we get a new formula which is still in OSC, and we can check it. And because OSC satisfiability is decidable, this makes also well-founded and finite satisfiability of formulas in OSC also decidable. And we also get a bound for model size under finite semantics. So this is interesting. In OSC, you don't have a bound for the size of any satisfying model. But if you're only interested in finite structures, you do have a bound for the size of a satisfying finite structure. Okay. On to evaluation. So we developed a prototype tool and that uses this construction of symbolic models and then finding induction axioms from them, and ran it on a bunch of examples with well-founded and finite semantics. We had 3 examples from distributed protocols that used well-founded semantics, 6 examples from reachability and linked lists that use finite semantics, and 6 other examples of node topologies in a network that used finite model semantics. All of these examples have an infinite countermodel under standard semantics, but we were able to find induction axioms in under 1 minute for all of those examples, and then verify them under their intended semantics. Okay, so to conclude, I've talked about how we use first-order logic as an abstract modeling language, how we use induction axioms to refine standard FOL semantics to our intended semantics, how we use symbolic models to automatically guide the refinement process, and I gave you some new decidability results for this OSC fragment of FOL. We have an artifact that is available through this QR code. And thank you. I'm happy to take questions.
Okay, we have about 4 minutes for questions. Please raise your hand if you have a question. And maybe hold your hand so I can see who's next.
Very nice talk. So I'm curious that I just look at your benchmarks. As you say you have paxos and do something on the linked list. All of this is a well-founded relation, just like a natural number or linked list. It's kind of not too complicated, right? People use this around as a natural number is not a very quite new idea, and the linked list, you have the induction structure. Maybe people already know it. So I'm curious about what kind of most complicated induction axioms you can infer in your system.
Okay, I think the axioms themselves that we use, and the general structure of the induction axiom was used before, like this, there exists a minimum value such and such hold. That's not new. But the process that we get by looking at a summary node, seeing what unary properties it holds, and then constructing an axiom, you get sometimes pretty complicated axioms, because we might say, well, I want all of these unary properties of the summary node and take the conjunction of all of them. And this can be, I don't know what's complicated, but it's not a very small axiom. It does involve many small parts. And also our generalization, where we take the unary property and replace some terms with free variables, also give rise to a bit more complex induction axiom, if that answered your question.
Oh, here's another question. Over there.
Hi, I'm interested in your experimental results. The induction axioms that you got, did you find them interpretable? What, like someone who doing proof by hand would end up with?
Yeah, so I think so. I mean, for example, the Paxos example, I think a human would also say, yeah, obviously the problem is that we need a minimal round where we vote, and this is the same thing that we get from our automatic process. In the linked list also, if there's like a problem where an infinite linked list violates some property, it would also say what you expect, that there's some maximum place in the list where this violation happens, and then it gets what you need. So I think it pretty much matches up what a human would do, I would say.
The screens, we have 1 more minute. Okay, one more question. Is the refinement process iterative? So you show that you have this symbolic model, and then you try to use it to get derive those axioms. So is it just one model that you're using to derive all the axioms, or do you get another symbolic model which is still infinite, and then you're using that one to get more precision?
Yeah, so great question. Currently, for our prototype, we only do like one round, one symbolic model. And I think our generalizations somehow help us to like get stuff that we would have gotten from other models. But it is totally possible to do this iteratively.
But you said the process is complete, so is it one symbolic model is enough to get the complete set of axioms?
No, it's not complete. No.
Oh, it was some for decidability. Okay.
Yeah, just for our benchmarks, we saw that it was enough to find the necessary induction axioms with just one model and this generalization of the unary properties.
Okay, cool. Thanks. So I need to switch.